All right, welcome back. We're going to continue with these logic slides. So we stopped last time learning about all the different logical combinators. There are more, but we learned the big ones, and or inclusive and exclusive negation. And then we manipulated those logical operations to build up bigger sentences with them, right? So we were talking about, okay, I've taken CSCI 41, but not CSCI 45. That's really an and with a negation. Yeah? So that's the kind of stuff that will soon become second nature to you as you get more practice on your homework and lecture and in the book, things like that. But let's keep on trucking. I have a little warm-up exercise for us. Let's pretend that I have given these values to these propositional variables. P is false, Q is true, and R is true. What is P or, and then in parentheses, Q and not R? Okay, so all these things together, but keep track of the parentheses. So what is the final result? It's always going to be true or false, right? But you tell me. So pause the video and try it. So assuming you're back now, let's just plug them in, right? P is false, so this is saying false. Oh, what am I doing? Sorry, my tablet was unhappy for a second. False or Q is true, true and not true. Okay, so we do things in parentheses first. So this is not true is just false, right? It flips it. So this is false or true and false. Do things in parentheses still, true and false. Well, they're not both true, so it's going to be false or the whole thing is false. Yeah, and that is false or false. That's the one way, right? Inclusive or, to make the answer false. So that's what we end up with. So the final answer is false B. Okay? So yell at me if that doesn't make any sense, but that is that's our first little example. Okay? So that is some good practice with what we just learned last time. And a lot of the time, it helps to make a truth table when you're not sure of the output. Okay? So, or you want to find all the possibilities. Let me show you how to write your own truth table for whatever logical formula you have in front of you. Okay? So if you're trying to show something, usually you save the final rightmost column for that thing you're trying to really get to, and then all the intermediate stuff goes to the left of that. Okay, so first you have the variables, then you have intermediate work, and then you have the final answer. And this will make more sense when I show you an example over here. So yeah, let me let's talk about all of this. So for example, let's seriously just do P or Q and not R. All right, so let's do that one. P or Q and not R. And let's try all the possibilities. We don't know what P, Q, and R. Let's see what would be true for all of them. Okay? So here's how you write this truth table. First you have P, all of its possible values, then Q, all of its possible values, then R, all of its possible values. That's the first thing. First you write all your variables out. And this is going to get ugly, sorry, because there's a lot to write. So let's scoot this over as far as we can. Let's do that. So that's the first thing. And then, I want to draw again, please. There we go. So let's just do it like that. That's P, Q, and R. So the first things that you write are your variables. All of those go first. And then you give all the possibilities for their combinations, right? So P, Q, and R, they could all be true, for example, or maybe P and Q are true, but R is false. All of these possibilities are fair game, so you have to try all of them. You have to write all of them. And let me show you how to do that. So there's a special order that we like to write in math for these variable columns. So you look at the rightmost one, and that one goes true, false, true, false, true, false. Okay, that's its pattern. True, false. There are 2 to the 3 possibilities, right? 3 variables, each with 2 options, true and false. So there are going to be 8 rows total. So we're going to go until there. True, false, true, false, true, false. Okay, so that's 8. And then we're going to do the same for Q, but the column to the left of that, the left of the rightmost one, goes, it goes true, true, false, false, true, true, false, false. So it stays the same twice. And then this is true, true. This is false, false. And this is the customary way of ordering these rows. And then the final column, the one to the left of that, goes, well, it stays the same for 4. It always gets doubled. So this is true, 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 false, 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 false. Okay? So this is the customary order, and that's how you can make sure that you get all of them. Okay? And so then our end goal, like over here, we're going to put that. Okay? We want P or Q and not R. And so to get there, we like to put our intermediate answer. So the first intermediate thing is let's do not R. We have R. We don't know what not R is. So let's include everybody. So here's not R, and let's try and make this straight again. So that just takes whatever's in the R column and negates it. So true over here becomes false. False over here becomes true. And so it's just getting flipped. False, true. Let's try and keep that in line. Oops. False, true, false, true. And then the next intermediate thing, because we want this whole thing eventually, is Q and not R. We just got the not R. Let's do, let's AND them. Q and not R. That's the next intermediate stage. So let's do that. Okay, we have not R, we have Q. Let's AND them together. True and false for the first one. True and false. That is false. True and true. That's true. False and false. That's false. And let me just do the rest quickly now. False, still false, true, false, false. So we have, it looks like 2 trues there. And then finally, we have P or Q and not R. Okay, and so then we can combine this and this. You see how we're building up the truth table slowly? In between here is our intermediate stuff. And then this is the final thing that we wanted. Final. So yeah, now we can use this row and, this column and this column and OR them together. So true or false becomes, in this possibility, in this universe, it's true. True or true, still true. So actually all 4 of these lines are going to be true first, right? Because it's ORed together. And then over here, these are false. So now it becomes, okay, what are these? So it's going to be false, true, false or false, false or true, false or false, false or false. So it looks like it's true these times and then this one time. Okay? And the one that I gave you was false, true, true. This one. And it was false there. Okay? So, yeah, any questions about any of this, let me know. That is how you write a truth table. All right? So you just keep on alternating, starting with true every 2 to the C rows, starting with C equal to 0. So you alternate every time. So alternate true and false once, every 1, every 2, every 4. And if you were over here, every 8, things like that. And then when we learn binary, or maybe if you already know binary, if true is 1 and false is 0, we're really just counting down in binary. 1, 1, 1, 1, 1, 0. We're counting up from the bottom. 0, 1, 2, for example. So that's kind of cute too. Okay? So that's that. Now that I've shown you how to do this, you try. Write a truth table for P and not Q. Show me all the possibilities. Okay? So pause the video, get started, and then I'll show you my answer. So we need values for P and Q. What are their possibilities? So true, false, true, false, true, true, false, false. And then we have P and, not Q, but another intermediate thing might be not Q, right? Let's do that. So false, true, because we're negating everything here. And then we can finally bring it together. P and not Q. So I'm going to AND together this row and this row. What's true and false? That's false. True and true. That's true. False, false. Okay, so it looks like it's only ever true once. If P is true and Q is false. All right, so that's the truth table. Hope you got that. There are definitely more logical operations than the ones that I just showed you last time. So let me show you the next, most important one. This is a very, very important one once we get into proofs. It's called implication or the conditional, okay? Because there's like an if statement going on. And you write it with an arrow. It's like P arrow Q. You might use two arrows sometimes. They're the same. P arrow Q stands for, I would read that as P implies Q, or if P then Q. We'll talk about it. So yeah, the idea is we want to be able to express conditions, things that might be true if something else is true. So like, if A is true, then B must also be true. We want to write that in logic. And so the first thing that we should probably do is like, what should the truth table of that even look like? We'll figure that out. And then we need to make a symbol. So the symbol is that arrow, okay? And the operation, we call it implication or conditional. It's just the fancy name for a mathematical if statement, if you will, okay? And so here are your possible symbols for it, and we're going to figure out the truth table together, because it is a logical thing to do, and we can figure it out, okay? So here is my example that's going to shed light on what the truth table of implication should look like for mathematical if statement. So let's say that Dad wants us to mow the lawn. He says he'll give me $20 if I mow it, okay? So we can write this in logic. We could be like, okay, here is mow the lawn, here's one proposition, and Dad giving me $20 is another proposition. It could be true or false, right? So let's make P, I mow the lawn, and Q, I get $20. And so I would like to represent or figure out all the ways in which I might get $20. I want to represent this fact. If P, then Q, okay? If I mow the lawn, then I get $20. That is a logical statement that can be true or false, depending on whether or not Dad is lying to me, right? So if I mow the lawn, then I get $20. P arrow Q, P implies Q. If P, then Q. You might hear me say all of those things, okay? So P is this, if I mow the lawn, and then Q is I get $20. Okay, so if and then. That's what the arrow stands for, if then. And the first thing, the if part, that's called the hypothesis, so if this is true. And then Q is called the conclusion. So if the P is true, then the Q is true. Yeah, that's the idea. And so let's figure out what in the world this truth table should be. What should it be? Question marks everywhere. Because we want our money, right? So P is I mow the lawn, Q is I get $20. Let's figure out what this truth table should look like in each possible case. Like, I mow the lawn, I get $20. I mow the lawn, I don't get $20, right? I don't mow the lawn, but I get $20, things like that. You see how I'm reading that? Those are all the possibilities. That's the universe, all the ways that things could play out. So think of it in terms of lying. So when would Dad be lying to us? That's when P implies Q is false, okay? So if we mow the lawn and we get the $20, then Dad wasn't lying to us, right? So P implies Q, if P then Q, should have been true. Yeah. So let's define it to be. If I mow the lawn and I get $20, well, yeah, Dad was telling me the right thing. If this, then that. Yeah, I did the thing, I got the thing. I got my money. So that is true. We need to figure out, like, when should P arrow Q, if P then Q, P implies Q, when should that be false? And the question to answer then is, when would we feel cheated and hate Dad? Like, when was he lying to us? That's when this is false. So, for example, this case should not be false, right? Because I didn't mow the lawn, but I got $20 anyway. Was Dad lying to me? I don't know. I didn't even try to mow the lawn, but I still got my money. So it should still be true, right? I'm not cheated. I got my money anyway. Isn't that cool? Thanks, Dad. Should this case be false? I didn't mow the lawn, and I didn't get $20. Well, I didn't uphold my end of the bargain, right? So I'm not sure if Dad was lying to me or not, because I didn't mow the lawn anyway. Sure, I didn't get the $20. So this we still say is true. This is the one case where we would feel cheated by Dad if we didn't get our money, right? That would be where we mowed the lawn, but we did not get $20, right? So obviously, him saying, if you mow the lawn, I'll give you $20, could not have possibly been true, right? You read this as if P then Q, right? It didn't happen. I didn't get the Q. It didn't follow from P. Why, Dad, why? So that's the one case where it's false, okay? When you did the thing, but you didn't get the result. When the hypothesis is true, but the conclusion is false. In every other case, it's true, right? It's true to say that if P is true, then Q is also true. In this case, it's like P wasn't even true. I didn't do anything. I didn't do my end of the bargain. And so I'm not even sure. Maybe it was true. So we just say that it is. Okay? Hopefully that makes enough sense. That is implication in a nutshell. And you think of it, you think of the false cases as when you would feel cheated. Like, what is the case where I did the work, but I didn't get my reward? Okay? That is the one time we felt cheated. Okay, so that is implication. Let's talk about all the things that we can do with implication, because it's a very powerful concept to have an if statement in math. So here are a bunch of different ways that you can use implication and manipulate it. Okay, so the converse of an implication of if P then Q is if Q then P. Just flip them. Okay, if you want to write the converse of an implication, you just flip the hypothesis and the conclusion. So this would turn it into, if Dad gives me $20, then I mow the lawn. So give me the $20 first, Dad. Okay? These are just fancy words, right? This is a fancy Latin word. The contrapositive of if P then Q, P implies Q, is not Q implies not P. So you swap and you also negate the hypothesis and the conclusion. So this would be, it would translate as this. If Dad doesn't give me $20, then I don't mow the lawn, okay? Which is, in fact, equivalent to the original statement, believe it or not. We'll talk about that. We also have the inverse of P implies Q. That is, not P implies not Q, or if not P, then not Q, okay? So that would be, you just negate the hypothesis and the conclusion, keep them in the same spot. And this would be, if I don't mow the lawn, then Dad doesn't give me $20. Okay? So you might think that all of these kind of sound the same. They are equivalent to the original, maybe. But in fact, logically, if you build out the truth table, only the contrapositive is equivalent to the original. Only then is the true and falseness for each row the same. That's what it means to be equivalent. And I encourage you to look that up. Okay? So we'll talk a bit more about this later, about equivalences. It is a very important concept, but do not be fooled. Only the contrapositive is equivalent to the original implication. All right? With that, I would like to talk about the biconditional. That is two arrows, one pointing to both sides. Okay? It's called the biconditional. It's sometimes written with the word if and then a second F, because why not? And you pronounce it as P if and only if Q, okay? It sounds weird, I know, you'll get used to it, I promise. But it's called the biconditional. P if and only if Q. That's how you read this, okay? So the reason it's written like this is P biconditional P, if and only if Q, it's equivalent to the following. And I should put parentheses, actually. Let me do that before I forget. It's equivalent to P implies Q and Q implies P. So both ways, right? So that makes sense why it has two arrows now, yeah? That is what it's equivalent to. It's equivalent to both this and this are true at the same time. And you know they're not originally the same, right? The converse is not equivalent. But we're saying that they're both true at the same time. P if and only if Q. And so there's an and going on. That's why we use and when we pronounce it. And the if part and the only if part are the names that we give to some of these. Okay? So the if part is actually this one. We say it's weird, but when you have an arrow going this way, this way implication, Q implies P, that is the same as P if Q. Why not? And the only if part is going from left to right. So that's the only if part. So there's the only if part, there's the if part. And that's why we say if and only if. You don't have to worry about that, though. That's just why we say that. So, yeah, P if and only if Q, it's equivalent to this. And if you build out this truth table, you'll see that this is true. The biconditional is used when you have two things that are absolutely equivalent. And this makes sense, right? So, true, true, the biconditional, this implies that and that implies that. It happens to be true when they're both true. If they're not agreeing, it's false, either way. And if they're both false, it's also true. So the only time it's true is when they agree. So the biconditional, you use it when you want things to be equivalent. You're trying to represent equivalences, okay? That means that their truth values correspond exactly. They're either both true or they're both false. They are the same. Isn't that nice? So true in both of these cases, but false if they ever differ. And that is, that might remind you of exclusive or. It's the opposite of exclusive or, isn't it? Because exclusive or, if we go back to it, that was true only when they differed. False otherwise. False when they were the same. The biconditional, if and only if, that's true when they agree, and false when they differ. So it's the opposite. So P, if and only if Q, is equivalent to the negation of P XOR Q. P exclusive OR with Q. Isn't that neat? So that's just another thing that we can have under our tool belt, and equivalence is a very powerful concept. Okay? So powerful that there's a subsection of your book and a whole section of these slides about equivalences and the laws that have to do with logic. Okay? So let's get into that, and that'll be most of the rest of today's content. Okay? So let's talk about all the different ways that we could have equivalences, or laws that we care about within logic. Okay? Let's talk about three important ones first: tautology, contradiction, and equivalence. Okay, so there's a lot going on here. Let me explain all of it. A compound proposition, so a proposition made of smaller propositions, it is called a tautology. It's a weird word. If the proposition is always true in every single column of the truth table. So for example, P or not P, that's saying like either P is true or it's not true. That is a tautology because it's always a true statement in the end. You could just replace that with saying, oh yeah, true. Everything is good. P, let me show you. Like here's all the values for P, true, false. Here's all the values for not P, based on P, false, true. Here's all the values for P or not P, just or them together. Oh, true, true. It's a tautology because they're both the same. Okay, it's always true, no matter what. So you could really just replace this by saying true, right? It's kind of like this is saying nothing, in a sense. So that's interesting. The flip side of that is you can have a contradiction if what you're saying, your compound proposition, if it's always false. Okay, so you can do P and not P, and that is always going to be false. P, not P, true, false. False, true, P and not P. Well, that's going to be false always, because one of them was false. All right? That's called a contradiction. It's like it's never true. There's no way to make this ever true. So it should be impossible, right? So that's interesting. You could have just replaced this with the word false. It's never, ever going to be true. So that's tautology and contradiction. And then let's talk about logical equivalence. So two propositions, two compound propositions, they are logically equivalent, we care about this, right, if they always have the same truth value in every column of the truth table. Like maybe it's like false, true, like one way makes it false, true, and then the other thing that you're trying to make sure is equivalent, it better also be false, true, right? That's what we want. And so we want equivalence. We want them to be exactly the same. We want to make sure that this is always true. Like these correspond, these correspond, these correspond, these correspond. They always have the same value. And you know what it means to always have the same value. The biconditional is always true. Does that make sense? So we want, or we can define equivalence to be this. Two propositions are logically equivalent when, if and only if them together, that is a tautology. It's always true. They always share the same answers, the same values on each individual row. Okay? So let me show you this. This is a law of logic. It is always the case that this is equivalent to this, no matter what the value of P and Q are. Let me show you that. All right? So we want to show that not P or not Q. Biconditional, if and only if not P and Q is always true, right? No matter the case, these are always the same. They're equivalent. It's a tautology. Okay, so let me show you that. So let's do the values of P, the values of Q. Let's plan this out actually. We got P, Q. We're gonna do. Let's just make it fast. Let's do not P or not Q all in once. Let's do that. Let's do not P and Q like that. And then let's do the final thing, the biconditional. So let's do not P or not Q if and only if not P and Q. And I'll show you why this all makes sense to say it like this. All right, so we had true, false, true, false. Sorry, this is a bit small. Now we have true, true, false, false. So what's not P or not Q? False or false, that is false. And then the rest is true, because this will make it true when you false, when you negate, when you negate, when you negate, and we're ORing. So these will always be true. And then this one, we're saying that it's equivalent, so we better also get this. So it's P and Q. Well, this is true. Negate that. It becomes false. What's P and Q? In all of these cases, it's false. If you negate that, it becomes true. Oh. So they do share the same value, no matter P and Q. Isn't that neat? And then, if we do biconditional, which makes sure that they correspond, right? If and only if, then this is true, because they're both false. They're both true. They're both true, they're both true. That's what it means. Or in this case, the output is true when they correspond. That's what it means to be in the biconditional. And so the output is a tautology, always true, which means that they were logically equivalent. They always shared the same output. You see how you can represent that now? And why it makes sense to say that? So logical equivalence is saying that between two things is taking their biconditional and making sure that it's always true. It's a tautology. Okay? So these are three very important concepts, and let's make sure that we have learned them well. All right, so what I'd like you to do is use a truth table to prove that P and not Q or Q with these parentheses, that's just equivalent to P by itself. So make sure that they're each row of the truth table lines up. Okay, you don't have to go as far as to prove that the biconditional is a tautology. You can just stop here and be like, okay, yeah, clearly they share the same values in every case. So please try that, and we'll come back and I'll show you my way. Or I'll show you my table. So we have P, we have Q, we're going to need not Q, we're going to need not Q or Q, we're going to need, these are all separate, we're going to need, and then the final one, P and not Q or Q. True, false, true, false, true, true, false, false. Negation of Q is false, true, false, true. Not Q or Q, true, 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 true is always true, right? That's a tautology. Oh man, we're not even at the end. We found a tautology. And then P and not Q or Q, well, true, true, you're just anding P with true, so it's just going to be whatever this side is, right? If it's true, yeah, true, true and true is true. If it's false and true, which is false. So it goes true, true, false, false. And what do you know? All these rows are equivalent to just P by itself. We didn't need to do all that extra work. So we could simplify the proposition into just P. That's nice. That's cool to know how to do, because this takes more computational effort. We could have just been doing P all the time. See how that's useful? So yeah, they're equivalent. And you could full out do the whole, like, if and only if, make sure that it's a tautology, but it's okay to stop here. We just notice that, okay, every value is the same in every row. Okay, so they're equivalent. Yeah, and this helps to motivate the idea of wanting to simplify propositional statements. So we have this, and really we could have just written P the whole time. It's simpler that way. So let's talk about ways to make things simpler, ways to make our logical formulas simpler. And one way to do that is to use De Morgan's laws. It's useful to use these fancy laws of logic, and they're just saying that this is equivalent to that, and it's usually nicer to work with one side of these. Okay, usually it's nicer to push the negation inward, we say. And that's what we want to do. And so this was invented by a man with the last name of De Morgan, and he proved some equivalences here. So they let us push a negation inside of a bigger expression. So if we don't like this negation with the or, we can bring the negation inside to the P and the Q, and it just so happens to flip the or to an and. Okay, not P or Q altogether is equivalent, logically equivalent to not P and not Q. Okay, and the flip one is true for the and as well. If you want to negate P and Q, you can push that negation inside of the parentheses, and it becomes not P or not Q. So it flips them. Flips the and to an or and the or to an and. And these are true things. You can go and use truth tables to prove that these are in fact equivalences, but we'll just take them for granted right now. And notice that P and Q, we have no clue what they are. They could be even bigger things, like P itself could have been like Z and not R or something. It doesn't matter. They could be as big as you like. You just keep following this rule to keep on pushing the negation inside to get to the variables at the end. Okay? So, with that, let's try simplifying this compound statement, this compound expression, using De Morgan's laws. So here is a negation, and it's negating all this big giant thing, and that's really ugly. So let's push the negation inside to both of the parts. And so it's this, really, it's this ORed with this right now. Let's push the negation inside using De Morgan's laws. Okay, we're going to use the law that tells us how to push inside of an OR, so this first one. So what you do is you negate both of these, and you flip the OR to an AND. Yeah, that's what it's saying. So this becomes, this is equivalent to negating X or not Y, and then this got flipped to an AND. So this was the P, this was the Q, right? And not Z and W, okay? And then we can do it once more, or twice more actually. We can push this negation inside and also this one. So we use De Morgan's laws twice more to get it all in there. Okay, so this becomes, we're using this rule now, one more time. So we push the negation inside, so we negate X and not Y, and we flip this OR to an AND. Okay, so it becomes, let's see here, not X and not Y. It's weird to look at. And then this stays an AND because we're done with that now. And then, let's see here. Then we got to do it for this one too. We got to use this De Morgan's law, okay, to push it inside of the AND. So this becomes not Z or not W. You see that? Isn't that nice? And then actually, two negations, that's another law that we'll talk about soon. Two negations become nothing, right? They just become the Y. Not Y is Y, not Z is Z. And so this is a simpler formula now. Okay, it looks cleaner. Don't have to worry about that weird looking negation out there. Okay, so that is De Morgan's laws. So you always you end up flipping these things a lot of the time. And this OR got changed to an and then you just negate both sides. And it makes your formula simpler. All right, and so these are nice to have, and there are plenty more where that came from. Well, these are laws of proving equivalences of propositions. Okay, so there's a lot of these. All right, they're useful enough to write down. So there's a big table in your book, and I copied that into these slides, and we'll talk about them. Okay, so here's a giant slide that we'll get to in a second. But the idea is every time you use these laws, every time you see one side of an equivalence, you can replace it with the other side because they're the same, right? Everything will still be correct. Everything will still have the same output because they are equivalent statements. Okay, we like to make things simpler. So let me show you, for example, silly example, but useful, that P arrow Q is equivalent to not P or Q. Can I steal some of these? Dun, dun, dun. Oh yeah, there we go. I'm going to show you this one. Yay. So this is just a law, actually. This is one of the laws, like, okay, P or P, that's just P by itself. You don't need it twice. Same with and. Associative laws, if you have two ors, it doesn't matter where you put the parentheses. It could be over there, over there. Commutative laws, you don't have to have P or Q. It could have been Q or P. Distributive laws get fancy. It's like multiplication distributing over addition. That's the kind of thing. It's like you have P or Q and R, that becomes P or Q and P or R. These are just a bunch of different laws that you will get plenty of practice with. But yeah, I encourage you to look at them. This is the double negation law, the one that I was talking about. If you and with false, it's always false. If you or with true, it's always true. If you or with false, it's like the false didn't do anything. It's just P. Same with anding with true. There's a lot of duality going on here. And what I'd like to show you is, let's prove that this law is true. This conditional identity is true. If P then Q is equivalent to not P or Q, in fact. It's weird to think about, but it is true. So let me show you that. So let's prove this particular equivalence, okay? Just to show you we're not lying to you. PQ, let's do if P then Q, and then not P, and then not P or Q. This is a very useful equivalence to know. So, true, false, true, false, true, true, false, false. And then we remember this one, right? It's only ever false if we did the condition, but we didn't get the conclusion. True every other time. Not P is just negate this row, false, false, true, true. And then we're going to OR this with this, so it's going to be true or false is true, false or false is false, true or true, and then false or true. And oh man, are they the same? Yay. So they are equivalent, and that's a useful thing to do to get rid of the implication so that then maybe you can use a De Morgan's law or something. It's quite nice. Okay, so these are very, very important laws to know. Okay, and so, yeah, we talked about a few of them. Distributive law, it's kind of like you're bringing that inside, just like multiplication distributes over addition. Associative and commutative, those are kind of like math as well. Like we know those. It's like the same as, it's saying like 2 plus 3 plus 5 like this. Well, that's the same as 2 plus 3 plus 5. No difference. Right? Where you put the parentheses. And then commutative is doing the same thing. It's like, okay, yeah, 2 times 3, that's the same as 3 times 2. No big deal. And so those exist as well in logic. That's all. Okay? So feel free to stare at this. I'll give you some examples though too. So what I'd like to do now, I'd like to have you do, is take this, either from the book or go back to the slide when you, or like rewind the video for a second. I want you to use these laws and tell me each one you use to prove that P and Q implies P is a tautology, which means it's equivalent to true, okay? A tautology just means that the statement itself simplifies to just true, okay? and I want you to name every rule that you use. So this is where you start. You got to end up with true. Okay? Show me all your intermediate statements. All your intermediate statements as well as which law gets you that one. Okay? So starting from here, P and Q implies P. Get all the way down to true. Okay? And tell me which law you use. So, pause the video, give that a try. Maybe I'll give you this slide. And then we'll come back and we'll do it together. All right? And I'll show you my answer. So, if you start with this, we need to get down to just true, which usually means we need to get rid of implication. Because all of these, like, none of these have implication anywhere. So let's get rid of it by using the conditional identity. Okay? So let's convert this to not P and Q or P, right? That's using the conditional identity. Because that's how we can replace. We replace it with the negation of this or with that. Yeah, that's all. So we just use that, and we set it, and then we do that until we get down to true. And so let's see what we can do now. So usually, if you have a negation like this, it's good to push it inwards to get that inside. And so we'll use De Morgan, okay? We'll use one of the De Morgan's laws. You don't have to say which one, but we're going to use one of these, the one with the and, so we can push that negation inwards, okay? So let's do that. We want to do that. So let's make that becomes, right? It becomes not P or not Q, or'd with P still. And that's De Morgan. And then, okay, we want to eventually get down to true. What can we simplify this with? If you look, we have a bunch of ors still, so the parentheses don't really matter. I have a P and I have a not P. Ooh, that's interesting. What if I get them together? Because if I had those just become true, right? P or not P. That is interesting. That is useful to have. Maybe that's what I want. All right, so let's try and get the P and the not P next to each other so that I can use, and parenthesize together, so that I can use this rule to make true. Because that's eventually what I want, right? That's going to get me closer to the answer, right? So let's try and get the P and the not P next to each other. So the first thing that we would like to do is move these, move the P to the other side of here, because then they'll be closer to each other, right? So let's change this to not Q or not P, right? Just flip where these are inside of that. Keep the P over here. And so we got there by boop and boop. We got there by using the commutative law. Okay. Commutative law for or. Yeah, still or. Commutative law. You see that? Now these are getting closer to each other. That's nice. We want them to be together, though. So let's change the parenthesization. Let's make it like this. Yeah? Because then they'll be next to each other. So this is not Q or not P or P with the parentheses like this. And we can go from here to here using the associative law for or. Okay? I promise you, with enough examples, this will become second nature. Okay? So that was an associative law. And then we want to use P or not P. It still doesn't look like this yet. We have to have the P on the left. Silly enough. So let's swap these using another commutative law. Not Q or P or not P. Commutative law. And I'm running out of room, so let's move it on up. Should I maybe make it smaller too? We could try. And then I can finally use my rule that makes it just true. This is called a complement law. I have P and I have its complement. And that just becomes true when you OR them together. Because it's like either this side is true or that side's true. One of them is, because you only have two possibilities. And then you've covered both. So it's automatically true. So this is not Q or true by complement law. And then, what do you know? Anything ORed with true is true. That's a domination law. True dominates when you're using OR. It's always true, no matter what not Q is. Oh man. And so this is just true by the domination law. And this is a proof. Okay, this is a way to justify that this is equivalent to this. We've said all of our steps. Okay, and so this is what I want you to be able to do. Okay, so yeah, pat yourself on the back if you got that one. But if you didn't, don't worry. You'll have plenty more examples of this, especially in your homework. Okay, so try this. Make sure you get it. And that is useful. You see how it's much nicer to just say true everywhere than this. Much less effort. So that's nice to have. And yeah, let's keep on trucking. So yeah, we're still recording good. The next thing that I want to show you is how to go from truth values to propositions. So kind of the opposite of what we've been doing. If somebody like gives you, or sorry, truth, yeah. If somebody gives you a truth table, there is something that you can do to turn it into a proposition, right? So like, I know these truth values. What in the world is the proposition that makes these happen? Okay, that's what I'm trying to say. So I'll give you a trick to immediately be able to find the proposition, and you'll be so cool at parties, okay? So the trick is, and there's a way to do it with just the false cases too. You might be able to notice that once I show you the way to do it with the true cases, but let's just break it down this way. I want you to extract all the true cases, okay? Like, we're not sure what this is, but what are all the ways that it was true, okay? So for example, like if your mystery proposition, if it's true when P is false and Q is true, then we're going to add something. We're going to say that our proposition is made up of this, okay? If P is false and Q is true, here is a statement that makes it so that that one case is true, okay? Does that make enough sense? So, like, it's true right now. That's one of the true cases when P is true. Or sorry, when P is false and Q is true, it's true. So let's add that case. So P is false, so not P and Q. Both of those are together to make this true case. Okay? And then there's another one where P is true and Q is false. That also is a true case. So we'll add P and not Q. I'll show you this. So if you just OR together all of those little sub-propositions, every time you see a true value, you have made the final original proposition. Isn't that crazy? So let me show you this. So here is P. Oh no. Here is P. Here is Q. Here is not P. And let me show you that not P and Q makes this one row, where it's only true right there. I'll show you how that's useful. Not P and Q. I want all of these. And I'll have some more as well. So true, false, true, false, true, true, false, false. And then not P, we negate. So false, false, true, true. Not P and Q. So take this and it with Q. That's going to be false, false, true, false. You see how this is a row, or a column, with just that one case that we extracted true. You see that? So if we ORed together a bunch of things that look like this, that's true only one place, then we'll get what we finally were after. Okay, does that make sense? Let me prove that to you. So that was the one. We just extracted that because we noticed that P is false and Q is true. That makes true. So that gives us this. And then if P is true and Q is false, that means we should also add P and not Q. Whenever it's false, you negate it. So if we add this row as well, and we OR those two together, OR this and this together, we get the final answer. Okay? So let's build that one. That needs a not Q, which is false, true, false, true. And watch this. P and not Q. True and false, false, true, false, false. You see how it's false everywhere except that one place that we extracted where it was true there. So we want to pick these out. And so with this one, we picked this one out. We made it just true right here. With this one, we picked this row out, and we made it just true right there. See how if we ORed together both of these, we ORed this with this, we would get this final answer, because it would be true from this one up here, true from that one up here, and false in the other two. That is how you can make this work. So this final answer should be not P and Q ORed with P and not Q. Okay, so it was each of these. Those each gave us one of the trues in one of the rows. If we just ORed them together, we'd have the true in both of those rows. Does that make sense? That is the secret. And then you can simplify it as much as you want using your equivalence rules, but this gets you a start. This is a valid proposition that exactly represents this mystery proposition. Okay, you found something for it. Okay, and it will make that truth table for you. Okay, and I know, yeah, this is just XOR, but I think you can imagine that if I give you a very fancy truth table, you'd have to use this rule to get what you're really after. Okay, so let me have you try it now. So here is your mystery proposition. It looks like this. This is what its output is for P and Q values. So what in the world should the question mark be? Go ahead and figure it out. Okay? So pause the video, give that a try. And then we'll do it together. Well, or I'll show you my way of answering it. So what you do is you extract the true cases. Here's a true row, and here's another true row. So let's represent what is true in those cases. So we're getting this particular row true because P is true and Q is true. So we're going to add P and Q. That's what makes this particular row. Okay, P is true and Q is true. That's how you can read this. And then we also have this true row coming from, made by, P being true and Q being false. So P being true and Q being false. That's how you can read that. And then this final answer is true when either of these rows are true. So you OR them together, and you have this proposition. That's what the question mark should be. And of course you can simplify it, but that is a start. Does that make enough sense? So please yell at me if that doesn't. But that's the secret. That's how you can take any question mark, any truth table, and figure out what proposition should have gone there. Okay? Using the variables at hand. So, I just want to briefly get into something called quantifiers, and we'll wrap up them next time, next week. But I want to get us started there, and I don't think we're going to actually get into quantifiers, but I want to get us set up for them. Okay? I want to talk about something called predicates. We've been talking about propositions. Okay? Propositions are just sentences that are true or false. Let's talk about predicates, which are a fancier step up from propositions. All right, so a predicate, it's just some logical statement whose truth value is a function. It's not always true, it's not always false. It depends on. It's a function of one or more variables. Okay? And once you apply the function, once you call it with real values, then you get a proposition. It's not true and false at the beginning. It's not true and false yet. You have to call this fancy math function. Okay? So that's the idea. So let me show you. Here's a predicate with two arguments. P of x and y. Let's define that to be true when x loves y. Okay? And this is some new notation. You'll see this in the book or in just future math textbooks. There's a bunch of different ways to make a definition of something. But remember, this is not like programming languages. This is not like a real equal sign. Equals with a dot. That is equivalent to, you might sometimes see it as equals with a def at the top of it. That is also equivalent to, it's just a definition. Okay, I'm defining something. when you make a definition, you might see that symbol. So I'm defining the predicate P of x and y to be x loves y. You see how it'll be true once I give an x and y value? Or, sorry, true or false once you give it an x and y value. So for example, P, Lawton cats, is true. Yeah? Because I love cats. And I can be x and cats can be y. And then it becomes Lawton loves cats. And that is a true statement. But it's not true that I like the smell of hand sanitizer, which is very unfortunate during the pandemic. That's a false statement, right? So P of Lawton and that is false. So the negation is true, yeah? Do you see how I'm using predicates? They're just math functions. They become propositions. They become true and false once you actually call them, once you fill them in with things, okay? That's the idea. And you can talk about the domain of a predicate. And that is just all of the different kinds of values you could give for the variables. It's like the types. So like this takes an int and a bool, for example, but it's a bit more general when you're using just math by itself, right? So for example, maybe we can say that we have to give that along with the definition, because you could fill it in with anything until then. So let's say that the domain of P is, or sorry, the domain of X is, let's force that to be only people. And then let's say that the domain of Y is just any noun. Okay? So that is us saying this is the domain of these variables of my predicate. All right? Just the set of all the different possible things that it could be. So X only gets to be people and Y can be any noun. Okay? That's the idea. So this is a valid call of that predicate, a valid call of that predicate. And yeah, we can have other predicates. We'd like to use P because it stands for predicate. But you could have like Q of X, R of X. Doesn't really matter. Yeah, for example, P of X, let's make that a predicate to be defined to be it's true whenever X minus 3 is greater than 5. Okay? So in this case, the domain of X could be, and we would have to specify because it is ambiguous, it could be only the integers. So like you're only allowed to say or ask about P of 42 or P of 0, for example. But you're not allowed to ask about P of pi because that's not an integer. Or maybe you're only allowed to ask about the domain of X is only every integer multiple of pi. So then you're allowed to ask about pi, P of pi, P of 2 pi, right? P of negative 42 pi. See how the domain changes the way you can interpret the predicate. Technically, P of 0 pi is allowed, but not like P of 3. Doesn't work anymore, etc. And this is called domain restriction. Because usually when you give a predicate, you just imagine that it works for anything that it could possibly work on, so like any possible number. But you can restrict that domain. You can be like, no, my predicate only works on the integers. No, my predicate only works on the integer multiples of pi. That's the only time you should ever think it makes sense and ask for a value or ask for true or false from it. Okay? That is the idea. So that is predicate in a nutshell. And it's useful because we can talk about higher level things using them with variables involved. And that leads us in to these things called quantifiers, which allow us to say like something is always true. Something is only sometimes true. We have the universal quantifier and the existential quantifier, which again have very fun new symbols that you have to learn and memorize. I'm sorry about that. It's just the way this class works. But they should make a lot of sense, and they have to do, or they're built upon, predicates, which you are now masters at. Okay? So that is where I want to stop today. Next time we'll come back and learn more about quantifiers, and then like really get into proving things. So then I'll lead into the next chapter as well. Okay? So that is where we're headed, but definitely get started on your homework. You have plenty of information to do many of those questions now. And I'm about to record the lab introduction video. So please go and look at that and get started on your lab because that will be due soon as well. Okay? And then remember that you have reading assignment 2 to be working on. So you're reading the first chapter of your Xi book. Okie dokie. That's the idea. So do all that, and I will see you in the lab video.